Hello students, in this video we are going to discuss a question from physical metallurgy related to crystal structure. In this question we have to calculate the number of broken bonds, also called as dangling bonds, and match with crystal structure and their planes. First we will go through the concepts like coordination number, dangling bonds or broken bonds, lattice points of different crystal structure. Then we will solve this question. What is coordination number? Coordination number of atoms that are directly touching or connected is called coordination number. Now we will understand this with the help of a diagram. Suppose that there is a 2D diagram in which a central atom is connected to 4 different atoms. Then these 4 different atoms 1, 2, 3, 4 are the nearest neighbors. These 4 bonds is called coordination number. Lattice point. A single point that represents a constituent such as atoms, molecules or ions. So position of these 4 atoms, this one, this one, this one and this one, is called lattice point. Now one by one we will take examples from simple cubic, FCC, BCC and calculate the number of broken bonds. Now we will calculate the coordination number of all these 3 structure: simple cubic, body centered, face centered. We can see that in 3-dimensional structure, for this connected atom there are 4 atoms, which is first, second in the left side, third in the top side, fourth in the bottom side, fifth in the behind and sixth one in the front. So the coordination number of simple cubic is 6. For body centered cubic crystal structure, suppose that this is the central atom. So we know that in body center the atoms are touching along the body diagonal. So this atom will touch to all the atoms present here because all these are body diagonals. So the coordination number of body centered is 8 because of 8 corner atoms. For face centered, if we extend this direction in 3-dimensional, the structure will be like this. If we want to calculate the coordination number of this yellow atom, we know that in FCC the closest pack is along the face center. So closest atom will be this one in the this plane, and 4 atom will be in the front side also. So in the plane there are 4 atoms. Just above plane there will be 4 atoms here also, and just like that there will be 4 atoms below as well. So the coordination number will be 12 for FCC. Similarly, the coordination number of HCP is 12. Coordination number for diamond cubic 4. Now after looking at the coordination number, we have to understand what is broken bonds or dangling bonds. So suppose that in 2D simple cubic crystal structure, the bonds are connected like this, 4 bonds. Atoms are present at all these centers. If we remove one of the atom from here, then number of broken bond will be 1. If we further remove one more bond from here, the number of broken bond will be 2. Similarly, we can remove all the 4 bonds equal to coordination number, and broken number of broken bond will be 4. Now defining the broken bonds or dangling bonds. It is the bond that are formed by slicing the crystal structure along any along any facets. Now we will see how to calculate the number of broken bonds. The formula for calculating the number of broken bonds per atom is given by N equals to Z minus number of in plane nearest neighbor divided by 2, where Z is coordination number, where Z is the coordination number. Suppose that this is X direction, this is Y direction, this is Z direction, and the first plane we want to calculate is for 100 plane of simple cubic. Then, so the number of broken bonds equals to, it is the coordination number of simple cubic. The coordination number for simple cubic is 6 minus number of in plane nearest neighbors. So in the diagram, we can see that there are 4 in plane nearest neighbor. So it will be 4 divided by 2. So the number of broken bond will be 1. Similarly, we will now calculate the number of broken bonds for all the 4 options. First of all, we will calculate the number of broken bonds for 100 plane. In the diagram, the 100 plane will be this. Number of broken bonds n equals to coordination number of FCC is 12 minus the number of in plane nearest neighbor. So in the figure, from the figure we can draw a separate diagram like this. If we place the atom here and now we want to calculate the number of in plane nearest neighbor, then in the same plane we can see at the there are 4 face center atoms present connected to nearest neighbor. In plane nearest neighbor atoms will be 4 divided by 2. It will be 8 by 2, that is 4 is the number of broken bonds for FCC. So for this option there will be 4 number of broken bonds. Now we want to calculate the number of broken bonds for FCC for 110 plane. Which will be 110 plane? The 110 plane will be this one. We can separately draw 110 plane like this. After drawing this diagram, from the diagram we can see that this distance is root 2a by 2, root 2a by 2, whereas this distance is a, this distance is also a. So nearest neighbor there are only 2 atoms present. So using the formula, now we can calculate the number of broken bonds. N equals to, what is the coordination number of FCC? That is 12 minus number of in plane nearest neighbor, that is 2 divided by 2. After calculating, it will become 5. So for option B, correct answer will be 5 number of broken bonds. Now we will calculate the number of broken bonds for FCC triple one plane. So which is the triple one plane? This is the triple one plane. Now we will draw the triple one plane in extended version. Now after drawing 2D extended structure, we can see that for a particular atom, the nearest neighbors are this one, this one, 1, 2, 3, 4, 5, and 6, which is at a distance of this one. And this distance, we know that half of side of the equilateral triangle, that is root 2a by 2. So the number of nearest neighbors in this case is 6. Number of broken bonds equals to Z, which is coordination number 12 for FCC, minus number of in plane nearest neighbor, that is 6 upon 2. After calculating, we will get 3. Triple one plane, number of broken bonds will be 3. Now we will calculate the number of broken bonds for option D. For the option D, the structure is body-centered cubic. Plane in this case is 110. So 110 plane is this one. After drawing this plane separately, you will get, so this is 110 plane of BCC. In this case, we can see that nearest neighbor in plane atoms are this one, this one, this one, this one. So there are four number of nearest neighbors. So for calculating the number of broken bonds for BCC 11 plane, n equals to coordination number, which is 8 in case of BCC, minus the in plane nearest neighbor are 4 divided by 2. So we will get 2 as the nearest neighbor. So for D case, we will get nearest neighbor as 2. So on matching, we will say that A matches to 1, B matches to 3, C matches to 4, and D matches to 2. So option is 1, 3, 4, 2. 1, 3, 4, 2. So option B is correct. Hopefully you understood the concept and you can now solve all the questions based on number of broken bonds. Thank you.